Hello everybody, my name is Charity and I'm a student teacher at the University of British Columbia, and today we're learning about organic chemistry. Awesome, let's get started. So before you start, you first have to understand, why is organic chemistry even important? Well, this is chemistry, right? So these are all the elements on the periodic table. If you haven't been able to see this before, you should take time and review and know not every single element, but know just the common ones that you'll see. For example, hydrogen, carbon, oxygen. These three are really important in organic chemistry. So if you don't understand hydrogen, carbon, and oxygen, please take the time, go review that before you start. Otherwise, you might be very lost as we start. Otherwise, if you aren't, other than these three atoms, hydrogen, carbon, and oxygen, you want to know probably the top 3 rows. So everything from number 1 to 18. So let's talk about chemistry. So what is chemistry? Chemistry is actually really complicated. You'll see lots of ways that an atom is represented. So for example, on here, we can look at a single atom. So what is an atom, right? So let's go look at some representations of atoms. These all look very different, but they're supposed to be an atom. And the reason for why they all look different is because no one has actually seen an atom or a chemical, right? So something really important to note is that everything we learn in chemistry is based on observations from what we can see with our eyes or measure with our instruments or in chemical labs, because we can't actually see something so small, because atoms are really, really, really small. In physics, you learn how small exactly an atom is, and the measurement is super small. Your human eye could never see something like that. Even like science instruments like X-rays, microscopes, they can't see atoms at all. No one has seen an atom or a chemical. So all we have been drawing, the ways we draw chemicals, the way we write our chemical equations, those are just ways of representing how the chemical or atom behaves. So now that you kind of understand that we can't see chemicals, but we're really just trying to understand how they behave, and using some of, like, we make up drawings and we make up ways of representing and symbols to represent these chemicals, right? For example, like hydrogen, it's an H. Obviously, the chemical doesn't look like an H. The atom is not an H shape, but we use the letter H to represent hydrogen. So before you start, we want to understand chemistry. So chemistry is defined as a branch of science that deals with the structure, composition, property, and behavior of matter. And this is what I've said before, right? Because what is chemistry at the end of it? We are not actually seeing, round circles with like a nucleus. You can't see that, right? What you do is, chemists, they look at how like oxygen behaves in the air, and they say, oh, oxygen has this, and this property, right? So this property, because it has this and this and this and this structure, and because it has this and this structure, this is how it behaves, and this is how we can use it in our, like, for example, in factories or to build cool stuff, right? So we really want to understand hydrogen and carbon, because hydrogen and carbon in organic chemistry are so important. They are the 2 most important atoms you need in hydrogen in organic chemistry. Let's start with hydrogen. So the reason why not all of there are some blanks is because some of these are too advanced, and I don't want you guys to have to be confused or think that you have to know this. So something to just know about hydrogen is number 1, right? So it is the smallest atom possible, right? So what it means is, inside the nucleus, it's 1 proton, and it's, in a normal state, hydrogen will have 1 electron, right? And so hydrogen is a very, very unique atom, because it's so small. It can move around very easily, so it doesn't get stuck. So that's why it's a gas at room temperature. Carbon, on the other hand, at room temperature, it's a solid. Not because it has only very little protons, because carbon has 6 protons. So 1, 2, 3, 4, 5, 6 protons in the center of the nucleus, And normally, to balance that positive charge from the proton, it will have 6 electrons floating around it. And that's still a relatively small atom, right? Like if you look at nitrogen, nitrogen has 7 protons. And 7 protons, well, that nitrogen is a gas, and nitrogen is the majority of the gas of the air we breathe. So why is carbon a solid? Well, that's because carbon exists in room temperature as a solid because it connects really well. So if you draw out the structure of carbon, you should draw out the structure of carbon in a Bohr diagram right now, and we will take a look at what it looks like. Now that you have paused the video, you have drawn out the Bohr diagram for carbon, which should look like this. So you can see that carbon will have 6 electrons. So the blue dots are the electrons, and the center is the nucleus with 6 protons. But the nucleus will never change. If the nucleus changes, it becomes a different atom, so we don't worry about the nucleus. So we can count 1, 2, 3, 4, 5, 6 electrons. So that is what carbon usually is. And you notice that on the carbon has 4 ways it can bond. It has 1, 2, 3, 4. So it can bond on 4 sides. So it's really, really stable when it bonds to other carbons, and it forms the structure that allows it to be solid. On the other hand, hydrogen is a single electron. So what it does, it's really good at bonding too. And it's also really good at leaving bonds. So hydrogen is like a basketball. Or like a ball that you play with in sports. It gets passed around really easily because all it does, it has one connection. Unlike carbon, which is more stable because it has to connect to 4 things. It likes to connect to 4 things. Remember, the valence rule is that it wants 8 electrons on the outside ring, right? It wants this to be filled, this to be filled to 2 electrons. This is already filled, and it also wants this to be filled. So what it really wants, it wants 4 more electrons. So usually it will try to go and share, right? For example, these are all bonding, where they are sharing electrons. As you can see here, the hydrogens, well, they only have 1 bond because they only have 1 electron. Their valence shell can only store 2 electrons. So it's really easy for hydrogen to bond singly to another. So before you start, you also want to generally know what polar covalent and non-polar covalent is. They're basically the same thing. They're all sharing electrons, as you can see here. But the only thing difference is that they're not sharing evenly. So for example, the water, H2O, it has 1 O and 2 H's. H2O is water. It's not sharing evenly. So what you can see here, hydrogen has an electronegativity, and oxygen also has an electronegativity, and their electronegativity is slanted. It's not even. So what it ends up actually being is the electrons are closer to oxygen because oxygen is a more electronegative atom than hydrogen. Electronegativity is not something we need to cover right now, but eventually you probably want to know this. So if you have questions about electronegativity later on, please make sure to ask your teacher. On the other hand, here, chlorine has the same electronegativity as itself because it's the same atom, right? So there's no difference. So the electrons are right in the center. They're not closer to one side or the other. Whereas for this one, the electrons will be closer to oxygen. Does anyone have, if anyone has questions, please make sure to ask your teacher. The other kind of bonding you will encounter is ionic bonding, right? So up here is ionic bonding, and you won't see ionic bonding in organic molecules. Usually you'll see a covalent bonding, but it's important to know the difference because ionic bonding can help you understand what is going on with the organic chemistry that you're doing. So ionic bonding is when you actually give away the electrons. Over here, you can see that atoms A and atoms B both have each have an electron from the other one, right? That's because they each want to have 8 electrons. So then, they can share their electrons right now. So they have been bonded. But over here, atom 1 and atom 2 don't actually have, they're not actually sharing the electron. See, over here, the red electron is entirely B's electron. So that gives atom B a very negative charge because it has more electrons than protons. and that causes it to be negatively charged. And while atom A has more protons than electrons, it becomes positively charged, and they are bonded because the charge attracts. They're not bonded because they are sharing electrons. They are bonded because the charges are attracting. So that's something very different that you need to understand the difference between ionic bond and covalent bond for your KCSE. Next, we're going to look at sort of like the bonding over here. So this is what like the bonding for a lot of like looks like. And you can see that we actually represent the bonding of chemicals very differently. So all of these, everything on this row, so H2, H-H, like this picture, all of these, they all mean the same thing. But again, because no one can see atoms, right? No one can actually see an atom. No one can see a chemical. They're too small for us to see. So what do chemists do? So scientists and chemists, they draw out symbols and they draw out ways to represent what they would look like. And because these diagrams, they help us understand why the atoms work like why they do, right? Obviously, there's not an H in your body, right? When you drink water, there's not an actual H. It actually looks very, very different. But because we draw out the electrons, we can see, oh, well, we understand why water behaves the way it does because it has the hydrogen and etc. It has these properties. On the other hand, if we want to write something, if we're writing a lot of chemistry, we're writing a lot of reactions, we need to be fast. We can't be drawing out every single dot, right? So then we use shorthand, right? So we use shorthand to represent H2. So what does H2 even mean? How do we know what's bonding? Well, we know that H only has one bond, and so we know the property of hydrogen must look like this and in turn look like this. And it really, it's, if we add the electrons, it looks like this. But, right, like for each one of these, this one is 3D, so it looks more like a pyramid than like in a line. And all of these are ways that you can see these atoms written out. So now we will begin looking at what you need to know about alkanes. Well, for alkanes, first of all, alkanes is a name for a type of chemical, right? So a chemical is really made out of a lot of atoms, right? You have combinations of atoms that have bonded together, that's a chemical. And so these are all the things you'll be learning today. So first of all, we want to understand a hydrocarbon. So here I have methane, which is an alkane. You will learn why later on. So, but we can see that we have a carbon and we have a hydrogen. And so what really hydrocarbons are, they're very 3D. So you can see that on the screen, we can only draw 2D. So what we do is like, we actually have to represent these shapes. And actually, like the basic hydrocarbon only has single bonds, right? So you can see that hydrogen, carbon, and each atom has one bond. So hydrogen is bonded to carbon by one bond. And it's very obvious to us because we know that hydrogen only has one electron. It can't share two electrons with carbon, right? And it is consisted of hydrogen atoms and carbon atoms. And that's why the name hydrocarbon comes about, because the first part is hydrogen and the second part is carbon. And so naming, if you have 4 carbons, it's butene. So there's no special things out of the basic hydrocarbon or alkane. So the basic hydrocarbon, right? Single bonds, hydrogen, carbon atoms, that is what is called an alkane. And we use that because we see alkanes a lot. And so we use shorthand. And over here, we have 2 carbons, but you can see that every atom here, you have 2 carbons, but the other atoms are all hydrogen. So this also counts as an alkane, but it's a longer alkane. And you can see that the carbons here are connected to each other, and they kind of look like this triangular shape, like a block, right? Because this is 3D, right? Like in how it exists in real life, it's 3D, it's not 2D, but it's really hard to draw that, right? So you can, the very special thing about this in 3D is that you can actually turn it. So you have hydrogen 1, hydrogen 2, hydrogen 3. You can turn it around, and then you get a different shape in 3D. And so this is the cool thing about like like chemists and drawing these kinds of pictures, it takes longer to draw, but it helps you understand how these atoms actually work. You turn them, right? So you can keep turning them around and then the shape will like rotate. But that's not something you have to know, right? So that's just one way of representing what it looks like in real life, right? Obviously, in real life, they are not these bubbles, right? These bubbles are just to help us understand the bonding. There are other ways for us to represent it. For example, there is a line representation, which is, this is benzene. This has a lot of carbons. Or you can have things like methane, right? So this is methane. We saw this earlier. It had one carbon, and this should be we have methane, which is actually hydrogen, 4 hydrogens connected to one carbon. And we can write it really fast, like CH4. But then we have no idea what the bonds look like. But because we know carbons must have 4 bonds to be happy, right? And hydrogens must have 1 bond to be happy. We know that this must be the structural formula. And it is true. This is the structural formula for methane, CH4. And the line bond representation, you can't represent it as a line bond representation. So this is the molecular formula. So then you have the molecular formula here. So these two are the same molecular formula. So you have CH3, CH3, and then, or you have bracket CH3 times 2. And these two are both molecular formulas, and they're short. So they're fast to write. It takes longer to draw out the structure formula. But once you draw out the structure formula, you really understand what is bonding to what. And the line bond representation is even faster because over here, all you do is you draw this one bond here and you fill in all the hydrogens. You assume all the hydrogens are there, right? So you have 3 hydrogens attached to this carbon, it's here. And you have 3 hydrogens attached to this carbon, and it's here. So the carbons become the ends of the lines and the bonds become really important in this line bond representation. And you can see that it can be really fast to draw, right? Same for this chemical, right? So you have CH3, CH2, CH3. And over here, you can write it in the short form, right? CH3, bracket 2, CH2. And so that what means, it means it has a carbon, 3 carbons, and 1 carbon in the middle is connected to 2 carbons, and it only, because it's already connected to 2 carbons, it only has 2 more electrons left to bond, which means it has to be connected to 2 hydrogens. So over here, you have 2 bonds. And so that's 1 bond, 2 bonds, and 3 carbons, which is 1 corner, 2 corners, 3 corners, right? And then you fill in all the hydrogens. So line bond representation is actually kind of hard to think about because you're looking at only the lines, right? The highlighted parts is actually the only things you draw. You don't draw anything else for the line bond. So you guys don't have to know the line bond representation. But what the line bond represents, what's showing you guys the line bond representation to know is to help you understand, oh, this is not actually what the chemical looks like. This is just a way that we draw the chemicals to help us learn, right? So if it helps us learn, we're going to draw it. And so the structural formula is actually the most useful thing to help you guys learn because it draws out everything out, but it's really long and it takes a lot of time. So that's why we will shorten it to use the molecular formula. So make sure you know the difference between the molecular formula and the structural formula because these are the two that you will be drawing on the KCSE. And again, here is the line bond representation. As you can see, the circles are the carbons and the highlights are the line bonds. Oh, let me pause the recording. Pause the recording right now and try to draw out the structural formula for methane, ethane, propane, butane, and pentane. If you weren't able to get that, that's okay. So we're going to look at an example of a hydrocarbon here. So hydrocarbon alkanes are known for a general formula of CnH2n plus 2. So what this formula means is that if you have n carbons, you will have 2n plus 2 hydrogens. Let's say over here, you have 8 carbons, right? 1, 2, 3, 4, 5, 6, 7, 8. Then your n will be 8 because you have 8 carbons. Then you will know that your hydrogens must follow this math rule. So you have 2 times 8 plus 2. So 2 times 8 is 16. 16 plus 2 is 18 hydrogens. So you know you must have 18 hydrogens. And if we check here, if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, we can see that this octane, this 8-carbon alkane, also has 18 hydrogens, just like the formula said. And so you want to remember this formula. And so alkanes, the information is that it mostly occurs in crude oil, natural gas, and biogas. This will also be oftentimes tested on the KCSE. You want to know that where alkanes come from. Nomenclature, you want to know alkanes and their names from 1 carbon up to 10 carbon. So you will be learning anything from carbon N equals 1 or N equals 10. So all of this is testable material. So some other things about alkanes. Alkanes are colorless. You cannot see alkanes, right? Alkanes are non-polar. And the reason for that is when we talked about polar bonding and non-polar bonding earlier, we talked about electronegativity. And what you need to know is that hydrogen's electronegativity and carbon's electronegativity is pretty much the same. So when they share electrons, the electron is pretty much in the side. It's not being pulled closer to carbon. It's not being pulled closer to hydrogen. It's pretty in the middle, right? Sorry. Let me change the slide. So earlier when I asked you guys to draw out the structure of methane, ethane, propane, butane, and pentane, now that you know the general formula, you can do it a lot easier. So what you do is actually methane is 1 carbon. So the meth part stands for the 1 carbon part. The ane part stands for alkanes, right? You see the cane, A-N-E, that's the same word here. And you can see that the ane stays the same for all of these because they are all alkanes. So they all have A-N-E-S. Ethane, the E-T-H stands for 2 carbons. So that will mean 2 carbons, and so you will draw out 2 carbons and then fill in the hydrogens with this formula. Or if you know that a carbon must have 4 bonds, it has to have 4 bonds, so then you will want to fill in 4 bonds. So because this carbon is already bonded to a carbon, we just have to fill out 3 more hydrogens, right? Propane, the P-R-O-P, stands for 3 carbons. Butane, the B-U-T, stands for 4 carbons. And pentane, just like a pentagon, the P-E-N-T stands for 5 carbons. So this is really important to know because this is testable, right? You're testable to up to 10 carbons, and we've only gone up to 5 carbons. So now we have more. So using the pattern from before, pause the video and try drawing out the structure formula and the molecular formula for these alkanes. Now that you have finished pausing the video, let's take a look at the carbons now, the alkanes. So we can see that hex, just like hexagon, stands for 6 carbons, right? Hexagon has 6 sides, hexane has 6 carbons, and it also has the ane, and you can see that all of these alkanes all end with ane. And then you have heptane, just like a heptagon has 7 sides, a heptane has 7 carbons. Octane, same as octagon, octagon has 8 sides, octane also have 8 carbons. Non-ane means 9, non is 9 carbons, and decane means 10, dec is 10. So these are all testable. So right now, obviously, it's hard to memorize, and I think the easiest thing to memorize would be this general formula. If you remember the general formula, you can calculate any of these. Or if you're really good, you can just look at the number, draw the number of carbons, and then draw out the missing bonds, because you know that carbons should have 4 bonds. So let's talk about alkanes, where they occur, right? So what is natural gas and biogas and crude oil? So let's talk about biogas first. Biogas is produced when organic products decay. And like, for example, like cows or animals or plants, when they decompose and they will, or even like past gas, right? They will produce methane gas in the absence of oxygen. If they have oxygen, methane gas won't be produced as much, but if they don't have a lot of oxygen, it would actually produce a lot of methane gas. And this is a crude oil deposit. So crude oil deposits are used to run cars currently. They're one fuel source for cars, and crude oil and natural gas can be used sometimes for cooking in your stove, or sometimes some stoves are natural gas and use natural gas. And so this is where you find crude oil and natural gas. So natural gas is actually found on top of crude oil deposits. So you can see in the ground, inside the ground, you have water, you have the crude oil, and then you have the gas. And then this is rock, right? So it doesn't escape into the air. And so then you have the oil well, which goes down and collects the oil and collects the gas. So natural gas is found on top of oil deposits, and the gas, again, it's mostly methane. So on the other hand, the crude oil is made of many different hydrocarbons or other non-alkane material. So this is a very big mix. It's very complicated, so we're not going to cover about what it exactly contains, but you can definitely know that some of the crude oil is alkanes. There are definitely alkanes inside the oil. So how do we kind of filter the crude oil, right? Because we have a lot of crude oil, which is a big mix. It's not pure, right? So we want to use a process called fractional distillation. So this is really important. And I think that you should draw down this diagram to help you understand how crude oil works, or fractional distillation of crude oil works. So because crude oil is a big mix, it has no single boiling point. When you boil water, because water is usually pure, the H2O has one state where it transitions from liquid to gas. But crude oil is different. Everything in crude oil has different amounts of carbons. As you can see, carbons from carbon chains, which is hydrocarbons, of 1 to 4, turn into gas when they are 50 degrees Celsius. So that's not very hot. Water will be hotter when you boil water. You have to get up to 100 degrees Celsius. And so for this methane, ethane, propane, and butane, you just heat it up to 50 degrees Celsius and immediately it is coming up and evaporating here. And so how this actually works is the crude oil is heated to 300 degrees Celsius. That's a very, very hot. So almost everything inside the crude oil will be gas. So we'll enter this crude oil fractional distillation tower. So that if it's gas, right? We're looking at a methane molecule. It's gas. Methane is going to be gas at 350 degrees Celsius. It's going to float. It's going to float up, 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 up. 200 degrees Celsius? Well, that's still very, very hot. Methane is still a gas. It's going to float up, float up, float up. 100 degrees Celsius? Well, it's still very hot. It's going to float up. At the very top, it becomes liquid, right? Or gas doesn't even become it. No, methane never becomes liquid in room temperature. So it's going to go all the way outside. It's going to go outside, and that's how they filter, right? Then you look at pentane to decane. So that's the other thing you need to know, right? So the pentane and decane will come in here, stay as a gas, stay as a gas, stay as a gas, and then at this temperature, it will become a liquid. So then the liquid falls because the liquid no longer can rise up, right? So it falls to the ground, the bottom of this thing, and gets filtered out. And the same thing for each of these long carbon chains, right? And so some of the uses of crude oil fractions is like smaller carbons are used for gas, larger carbons are used for petrol, kerosene, light diesel, diesel oil, lubricating oil, and asphalt, right? Asphalt is what the really, really dark roads or really, really big roads get. And all of these have good uses. So you can write some of them down if they seem relevant to you. We talked about boiling point, right? We noticed that different lengths of alkanes had different boiling points. So first, we looked at methane, right? Methane had a very, very low boiling point. What that means is when it becomes a gas, it's a very, very low temperature. So methane at room temperature in 20 degrees Celsius or 30 degrees Celsius, it's a gas. However, decane at 30 degrees Celsius, it's a liquid because decane is a lot bigger. And we're going to explain sort of why. So you notice here we have a lot of methane particles. And then here we have 2 decane particles. You can see that Methane is a lot smaller. And so when it bonds, it's not very good at sticking with these bonds. However, decane is very big. So as soon as it comes close to another decane, it makes really, really strong bonds. Because look, it has 10 carbons. And then also up here is 10 hydrogens. And down here is another 10 hydrogens. And around here is 2 hydrogens. So it makes a lot of like momentary bonds, intermolecular forces. These forces are called van der Waals forces. The specific name is called van der Waals force. So these hydrogens make van der Waals force intermolecular connections. And they're not bonds in the sense that they're not covalent bonds. They're not sharing electrons, but the electrons kind of interfere with each other and kind of help bond these atoms. And so these two will stick much closer to each other. And so if we think about the definition of a gas, a liquid, and a solid, gas, the molecules are spread out very apart. In the liquid, they're kind of close together, but they can move, right? Just not very well. They're generally still kind of attached. But a solid, they're very, very solid together. So over here, we can see that the methane, well, they're so small, they can move around very easily. But then the decane, because it has so many intermolecular forces, it's a bit slower to move around, right? And so we can see that it needs more energy to become a gas, right? So this is very important for melting point and boiling point, which is when the melting point is when the states change, right? So the melting point is when liquid methane becomes, or solid methane becomes liquid methane, and or solid decane becomes liquid decane. Boiling point we already covered is when you go from a liquid to a gas. Melting is from a solid to a liquid. Viscosity is a new word that you might not have heard. What it really means is how fast things move. For example, if you look at water, water moves really quickly, right? You can swish the bucket of water around and it'll move very quickly. But if you have oil, oil moves a lot slower. Oil, if you shake the bucket, it doesn't splash as much as water does, whereas water will splash. Then you have flammability. So when it burns into fire, how easy is it to burn? And then you have density. Density is really how heavy it is in water or in other liquids. So in liquid form, how heavy is this? So if you put liquid methane on top of liquid decane, which one would float and which one would sink? If you put oil on top of water, the oil would float in a layer above the water, and the water would be floating in a layer below the oil. Finally, you have solubility in water. So all alkanes are not soluble in water, but some of them are more soluble in water than others. So here we have we can see that the top four are mostly going to be very close to each other because they're all very small, right? So you have the top four, because they're so small, they have certain properties that are similar to each other. So they become liquid a lot easier because they're a lot smaller and they can move around faster. They become gas a lot easier. Also the same logic. They're smaller, they can move around faster. Viscosity, can it flow down? Does it splash? Yeah, it's a lot faster to move around. Same logic. Flammability, they're the most flammable. Density, they're the least dense. That makes sense, right? They're the smallest, they'll float. And soluble, they're the most soluble in water. Because water, like we mentioned before, water is H2O, which is a polar molecule. So a polar molecule means that it doesn't share its electrons evenly. So water has a small negative charge on the oxygen and a small positive charge on the hydrogen. However, alkanes are nonpolar. If you remember from the physical properties, alkane properties was nonpolar. So nonpolar materials are not very soluble in water at all. However, in comparison, methane comparison to decane, methane is smaller, so it will fight water less. So it'll be easier to be soluble, but overall, alkanes are not soluble in water. So this is just in comparison. So make sure that this one, it's really special. Alkanes are really not soluble in water, but just in case they ask you the difference between methane solubility in water versus decane solubility in water, that's the difference because methane is smaller. On the other hand, you have these really long alkanes, right? So because they're so long, they'll move around slower. It'll be harder to move around because they're having these van der Waals intermolecular forces. If you aren't sure about intermolecular forces, make sure you pause the video and ask the teacher. So obviously you have 11 plus carbons. You don't have to remember that. Now let's talk about the homologous series. In this point in the lesson, you've already been really familiar with the homologous series. You can see the definition here, but really what it means is you have methane, and then the next one in the homologous series is ethane, and the next one is propane, the next one is butane, the next one is pentane, hexane, heptane, octane, and then not pictured here is nonane with 9 carbons, and then decane with 10 carbons. And it can keep going on, but what you really know is that if they ask you what we want to go from 1 carbon to 10 carbons, we go in a series, and the series is called homologous series, and they are represented for alkanes in this formula. For alkanes, there are 2 specific reactions that you have to know for the test. One is combustion reactions. This is fire, right? When you burn, how flammable is it? When you burn it, what happens? And then 2 is substitution reactions. We'll get into that later. So combustion reaction. We can see here that this is your formula, right? You have an alkane, right? You have X amount of carbons, and then you have Y amount of hydrogen. And then you add that to some gas. So this usually will be a liquid, unless it's like methane, for example, methane is a gas, then it will be a gas, right? So this is not always a liquid. So depending on the size of your carbon chain, right, this will be a gas. Depending on its boiling point, this will be a gas or a liquid. But either way, it is an alkane and an oxygen. And then you add heat. And then this part is really important for you to remember. You should write this down for combustion reaction because this is your reaction. You will always produce CO2 plus H2O when you have enough oxygen. If you have enough oxygen, you will produce water gas, so water vapor, and you produce carbon dioxide vapor. Can anyone tell me where else do you see carbon dioxide? Unpausing the video now. Carbon dioxide is also something we breathe. So water and carbon dioxide, they are all really good. They don't actually hurt humans. However, why do we talk about carbon dioxide being a bad thing for the environment? Because we humans breathe out carbon dioxide all the time. Well, that's because carbon dioxide is a greenhouse gas. Just like methane, it forms part of the ozone layer and it blocks sunlight inside the earth. So then it causes the earth to heat up. And so that's why we want to if we do a lot of combustion reactions, we are producing a lot of carbon dioxide. But carbon dioxide is not poisonous to humans. That's not the issue here. The issue is that it becomes part of the ozone layer in the atmosphere, and it becomes a greenhouse gas. That's why we want to do less combustion reactions. If we want to do combustion reactions, we don't do too much all at once. However, if you don't have enough oxygen, what ends up is you have no more oxygen to use here, right? Obviously, water, you need oxygen to be produced, right? So you're going to give an oxygen here, but carbon dioxide is actually ending up going to be carbon monoxide. So you're going to get rid of one of the oxygens here because you don't have enough, right? If you put it in a very oxygen low environment, you end up with carbon monoxide, and carbon monoxide is poisonous to humans. So it's very bad. It will kill you. It was very poisonous and it will hurt you, and then you will get very sick. So when these alkanes happen in the combustion reaction, they burn, right? All alkanes burn blue, right? So they burn a blue color in air. So here we have an example of 3 examples. Please pause the video and try these examples out. Draw the combustion reaction for methane, for ethane, and for pentane. Unpausing the example now, we can see that this is the answer. So obviously, I'm going to walk you through the answers. This is not the balanced reaction. So far, we've gotten the formula correct, right? This is what you put into the reaction. This is the reactants. You have to add oxygen, which comes in pairs of 2, right? In the atmosphere, oxygen is always connected to another oxygen. And then you have the products. which is always going to be carbon dioxide, and hydrogen, dihydrogen monoxide, which is H2O. So now we're going to start balancing. First of all, here's the strategy. Because you have only one place where you have carbons, we're going to start with that, because that's the easiest. You have a lot of oxygen, you have a lot of hydrogen, but you don't have that many carbons, right? So let's start with the carbon. So you notice here that this is 1 carbon, this is 2 carbons, 5 carbons. So we write 1, 2, 5. That's the coefficient. That's going to be your multiplier. Then we move to the hydrogens, and that's another strategy. You start with the carbon, then you go to the hydrogen, and then you try to balance out the oxygen, right? So you look at the hydrogen. This is easier because hydrogen only appears on one side, whereas for oxygen, you have to consider the oxygen in CO2 and the oxygen in H2O. So that's why we go to the hydrogen next. So after we balance the carbons, we look at the hydrogen. And we also know that hydrogens only appear on one side here. So we do 4. We have 4 hydrogens right here. So then we do 4 divided by 2, right? So we have coefficient of 2. 6 divided by 2, coefficient of 3. 12 divided by 2, coefficient of 6. This is all very good. If you have questions until this step, please ask your teacher. The next step is going to be the hardest step in balancing the equation. And this is a step that you have to go really careful and be sure of your math, right? So now you're going to look at your oxygen. So this is how many oxygen you have on this side, right? So for methane, the methane combustion reaction, we see that we have 2 oxygen in CO2, and you have 2 oxygen here. So, or 2 oxygen here. And so that adds up the 4 oxygen on the product side. And then you will want to balance the same amount of oxygens on the reactant side. So do 4 divided by 2, and then you have the coefficient 2. The reason you're dividing by 2 is because you have 2 oxygens here already. So you have to be multiplying by this 2 anyway. Let's skip ethane, and let's go down to pentane. So here you have 10 oxygens because you have 2 times 5. And then you have 6 oxygens, and you have 6 times 1. So 10 plus 6 equals 16. 16 divided by 2 is 8. That is very easy. However, going back to ethane, you notice that ethane is a very strange molecule. It is a molecule that ends up having 7 oxygens on this side. So you have 4 oxygens for CO2, and then 3 oxygens for hydrogen. And 7 divided by 2 is not very good. So either you write 7 divided by 2 here, or if they ask for a whole number coefficient, then you have to do something different. And the rule of thumb for this whole number coefficient is you add a 2 over here, because you double the amount of carbons for combustion reaction. So you want to double the amount of carbons. So now you have 2 ethanes. Then you have to change all your coefficients for here too. So you have 2 ethanes, then you have 2 carbon dioxides, and then you have 12 hydrogens. So then you have 12 hydrogens here. And then here you finally get an even number. So you have 4 plus 6 equals 10, and then 10 divided by 2 equals 5. Please take time to review making the coefficients and try it out for yourself. Continuing on, we will talk about substitution reactions. So UV light is required to start a substitution reaction for alkanes. This is really important. If you don't have UV light, the substitution reaction will not happen. So this is one big thing. You will be asked on the KCSE sometimes, what do you need for a substitution for an alkane to happen? And this is the thing, you need UV light. So what is a substitution reaction, right? So we know what a combustion reaction is because it's just burning. But substitution reaction is switching up connections. But we're not changing a connection, we just switched the atom. You see from atom A and atom B, they already have a connection. But the result is atom A switches to connecting with atom D. And atom C switches its connection from D to B. And that's a substitution reaction. You didn't really change the structure of the atom, but you just switched out something. So here you can see a very common substitution reaction for methane. So for substitution reaction, our example is using chlorine. Chlorine comes in Cl, bonded to Cl. And what you see here in the product is all you did was switch out this hydrogen for a chlorine. switch out chlorine for hydrogen. So that's the substitution reaction. It's super easy. But however, one really important thing, you never switch the carbons. You only switch hydrogens, okay? So only switch hydrogens. Never switch the carbon. And that really is important because otherwise, if you switched out the carbon for Cl, chlorine, you would get a very different structure because chlorine also likes single bonds, right? Carbon wants 4 different bonds. Chlorine wants 1 bond. They are all single bonds, but carbon wants 4 bonds. Chlorine only wants 1. You can also replace chlorine with fluorine or bromine, right? So all you have to do is change the chlorine to fluorine or bromine, and then you would do the same thing. You would also only switch hydrogens. You would never switch the carbons. So please take the time right now to try out this example. So here you already have a carbon with a chlorine, and then you're trying to, in UV light, you're trying to do this reaction. Pause the video now and try this out. Unpausing the video, we see, oh, it's the same thing. All we do is we take one of the hydrogens and then we switch it out for chlorine. Super simple, super easy. Never touch the carbons, just switch out the hydrogens. And so the 2 really important items you want to know for substitution reaction with alkanes. Alkane substitution reaction is, it requires UV light. And the chlorine and bromine are the ones you need. What you would name for chlorines is all you do, you add the chloro stuff, a prefix in front of the word alkane. So for example, for methane here, this atom is called chloromethane because it has 1 chlorine in front of the methane, right? Same thing for bromine. So you add the prefix bromo in front of the alkane, right? So here, if this was a bromine instead of a chlorine, you would call this atom bromomethane. And again, UV light, very important. And the sun counts as UV light because the sun's rays has many rays. It has visible light and it has UV light. So if you do it inside sunlight, with enough UV light, yeah, this is a reaction that's possible. So next we'll talk about school lab preparation of alkanes. So this is something really important about the lab that you never want to do. So in a lab, you can see this student is leaning on the table and looking over. His eye is directly above the flask, and there is material inside the flask. This is very bad because if you can see, if the material suddenly makes a reaction and comes out of the flask, where is it going? Yeah, it's going directly into their eye, and then their eye can't see anymore, right? So it's very dangerous to do this. So never do this, okay? This is just a safety tip that most students get wrong. Other safety tips, they don't get wrong as often, but this one, they just like to look over. So always never look on the top, from directly top. Only look from this side, okay? We're going to look at a video of using a school lab to prepare methane. Unfortunately, we aren't able to prepare methane in your school. However, all you have to know is the basic reaction and basic setup. And this can help you later on in university when you do labs, if you want to do chemistry in university. So let me mute myself. Awesome. Excellent. So looking at this laboratory setup, you have your sodium ethanoate in the video, or we're later going to look at propanoate. So this is for alkane. Notice how the A is important. So because we are looking at alkane. And then you add sodium hydroxide, which is soda lime in the video. Right? So you have heat. You heat up this tube, and inside you have these two chemicals. And that goes into the tube, and it goes down, it becomes gas. It goes into this tube. It goes down through the water, and then through this inside this pipe, it will float up because it's a gas. It's a bubble, so it'll float up and be collected up here through the water. So here's the template for preparation of alkanes in lab. So here you will see that you have a template of CnH2n plus 1, whereas for alkanes, you'll get an alkane of CN2n plus 2. And you notice that you have over here added COONA, and this is NaOH, which is your soda lime. So you always want to start with a sodium alkanoate, adding a soda lime, becoming an alkane, and then what you get at the end is sodium carbonate, which you don't want. So this is solid. So in the video, this is being collected down here because gravity is very heavy. The solid soda carbonate will stay down here, but the methane and ethane will be floating up here and be collected up here. So here you can see the structure of sodium alkanate. So you have the sodium, which is the Na, and you notice that this is an ionic bond because there are charges here, right? And over here you have the COO part of this is the sodium alkanoate, OATE. That is the C double bonded to the O and single bonded to the O minus. And then you have the alkane side. This is the alkane. This looks very similar to an alkane, except it's missing that last hydrogen. So we will start with sodium ethanol. To prepare methane, you require chemicals, which is your alkanoate from the previous slide. And methane, you notice that in the video, they use sodium ethanoate to create methane. And that's very interesting because ethane, you think methane, well, you just need methanoate, but that's wrong. You need ethanoate. And you notice how ethanoate has two C's because it has the ETH, so it has two carbons, and methane has one carbon. So you need two carbons, sodium ethanoate, to produce methane. And to produce methane, now we go on to produce ethane. So ethane, this is ethane because it has two carbons, but to produce 2-carbon ethane, you want 3-carbon sodium propanoate, right? So you have 1, 2, 3 carbons to produce ethane. Now, before I write to prepare propane, please list out the reactant agents when I pause the video. Unpausing the video now, you will need soda lime, you need water, and you need sodium butanoate because butanoate has one more carbon than propane. So here you can see sodium propanoate, ethane, sodium butanoate, and propane. So sodium propanoate will become ethane, sodium butanoate will become propane. That's because you cut off. Can you see? You can cut off this bond. You will keep the COO, but you'll cut off this bond. And over here, you'll cut off this bond. So you have 3 very similar alkane. This is very similar to an alkane here, right? Because you can see there's just carbon and hydrogen. And you ignore the whole thing attached to the 2 oxygens. Again, looking at the homologous series, right? We just go off the homologous series, right? This is where the homologous series comes right. It's interesting, important around. So, using your formula to write out school lab preparation of alkanes, please write out the chemical equation for how to produce methane, ethane, and propane. Please pause the video now. Unpausing the video now, we will see that this is the equations. So again, you can see that this H ends up being added to the CH4, right? You have CH3, right? Remember, we were missing a hydrogen on this side. So that's where the soda lime provides the hydrogen to come on this side. Same thing here. Soda lime provides the hydrogen to join. Because then you have CH3, CH3. Seriously. Same thing. Hydrogen moves over here. And then the COONA moves over here. So what do we use alkanes for? Why are they important? Why are you learning about them? So most alkanes are used as fuel. So methane is used as a biogas at home, and butane is used as a laboratory gas. It's very useful for burning. Remember, these small gases are very flammable. On cracking, after you crack, alkanes are a major source of hydrogen for the manufacture of ammonia in the Haber process. And this is a process you will learn when you learn about nitrogen. In the manufacture of carbon black, which is what you produce, important for printing out. So when you print out your test in the ink, that's the important part. And you also have lots of industrial chemicals, which are methanol, butanol, chloromethane, all sorts of uses. So there you have it. Please pause the video right now and review all of them. It's best to review them today, immediately after the lesson. Otherwise, it's very easy to forget. Pause the video now and go through each of these points and think about, remember what they were.